We are Team Articulex presenting the M5 benchmark. Since the release of ChatGPT, NLP research shifted to large language models and their multimodal counterparts, LMMs, that accept images and text are instruction tuned. Current LMM deliver strong performance in English but fail across many other languages and cultural context. The current performance benchmark are either text only or multimodal but monolingual, so they do not measure multilingual, multicultural vision language ability. That gap produces large systematic performance disparities and cultural blind spot in deployed models.
Hello, my name is Dhruv Goyal and I am presenting the related work and the how this paper is different from the existing papers in this M5 paper. So there were many benchmarks like Big Bench, Helm, MMLU, which were focused on text only. So and all the data was in the English language. So it was monolingual and monomodal. But after that, there came benchmarks like Mega, Megaverse, MultiQ, which were multilingual, but they were only focused on the text data. So they were not multimodal. Then comes the multimodal benchmarks later on, like MMMU and MME and MMBench. But the primary language used was only English, and some tasks were in Chinese also. But like it was not a type of multilingual; it was only multimodal. But there was at last a benchmark named IGLU, which was multimodal also and multilingual also. But the main disadvantage was that it only evaluates on the non-auto-regressive transformer encoders only. Like we can take the example of like non-auto regressive transformers are like they do not make the embedding answer in token by token, but they give the answer in one token only. So it is good for the classification type of problem, but not in the free form making like image captioning or like image like getting the text from the image. In that task, it fails. So mainly the task which were in Igloo was mainly the one like a classification type of problem. But after that comes the M5 paper, which was different from these because it was the first ever large scale paper, which was multilingual, multimodal, and also multicultural. And also it had five tasks, uh, five different type of tasks, and it includes 41 unique languages, mainly from Asia and America and Africa. It had eight datasets covering diverse images, and it was evaluated over 18 LLMs, different LLMs like ChatGPT, Gemini, Grok, not Grok, like it came later. But the main advantage was that in this paper, they made two new datasets named M5-VGR and M5-VLOD, which in which the mainly the languages were Asian and African. And other than that, the data set was taken from the Dollar Street data set, which is like freely available and and has many culture from different countries. So that's why it was like multilingual, multicultural, and multimodal.
Contribution of M5 paper. So the first contribution of M5 was the benchmark itself, the first multimodal multilingual benchmark, which had five tasks in total, created from out of eight data set, which had 41 languages. The second point was the two new data set that they have curated on their own. So the M5 VLOD and M5 VGR, their focus was under the 10 underrepresented African and Asian languages, including English and German. The images depicted the respective cultures where the languages were spoken. The third contribution was the new task VLOD, which is visual linguistic outlier detection. So given five images, the model had to pick the outlier one. The fourth point of contribution was the comprehensive evaluation that they have done on 18 large language models or large multimodal models. And the fifth one, the public release of codebase and dataset. Methodology, tasks, and datasets. The first task was visual question answering, in which the model was model was given an image and a question, and the model had to give the answer in a one-word type of format. The second task was visual grounded reasoning, a binary classification task. Given two images and a hypothesis, the model had to tell true or false based on the if the hypothesis is correct for the images A and B. Third task, visual natural language inference. This was also a binary classification task. Given an image A and a hypothesis, the model had to tell whether the hypothesis is contradicts with the image, entails with the image, or is neutral with the image. The fourth task, which is new one, visual linguistic outlier detection. So this was a multiple choice type of task. Given five images and a hypothesis, the model had to pick the outlier one based on the hypothesis. The fifth one, image captioning, which is a free text of type of task. So given an image, the model had to generate its caption. The new dataset, M5-VLOD and M5-VGR. So the focus of the curation of this dataset was 12 underrepresented languages, which had 7 scripts. The data annotation was done by professional annotators, so they hired professional annotators, which were native to the respective languages. Also, to make sure that the quality of the annotation is fairly good, they repeatedly inspected some random samples and translated them to English and then gave feedback. Gave feedback. Culture diversity. For considering culture diversity, they have taken the images from Dollar Street data set, which has around a total of 38,000 images taken in 63 different regions, and each image is tagged with one or more topics, uh, which they have used which they have used to curate the data set, to curate the image basis. The How they have created the image basis. So they have sampled a subset of images from for each language and each topic, and then further created a uh, a pair of images based on the data set.
They evaluated 18 LLMs across 10 families with diverse model sizes ranging from 3 million to 40 million. They considered both open source LLMs and proprietary LLMs with diverse architectures. For evaluation, they used several matrices such as for classification tasks, they used accuracy. For image captioning, they used BERT score often and CHRF++. BERT score often gives higher score when semantic similarity is higher, and CHRF++ gives higher score when character level similarity is higher. For language fidelity, they used GLOT LIDV3, which gives higher score when input and output both are in same language. They chose zero point 0.5 as baseline for binary classification task and zero point 0.2 as baseline for outlier detection task. They evaluated models on English and non-English datasets, and so that when we go from English to non-English, we see a drop of 0.02 on almost all models, except some models like GPT, AMBLIP, because they are trained on diverse data set of multiple languages. But we see a significant drop in small models like AMAXM, AXM 3600, because they are mostly trained on English data sets. They analyzed that large models not always perform better on all the tasks. Although some proprietary models like GPT and Gemini perform better on the tasks which are complex, but when a small model is trained for a specific task, it converges the accuracy. And even if we go for a larger model, it doesn't always improve the accuracy significantly. They divided the languages into multiple classes. The higher class means the language has higher resources, and lower class means it has low resources. When we go from higher class to lower class, we see a significant performance drop, which shows that the languages which has low resources, the model underperforms on that. In the data sets they created, M5-VGR and M5-VLOD, they took the data from dollar state images which contain images of 63 globe regions. They especially considered the 12 underrepresented languages and show that on that languages, the model just performed near to random baseline, which shows a poor performance on low resources languages.
Looking ahead, our future work focuses on addressing key limitations of the benchmark. First, for multilingual captioning, we need fair language agnostic metrics that move beyond tokenization and n-gram overlap and also correct the biases of the embedding based metrics by using stronger multilingual semantic models. Second, for visual question answering tasks, we must design evaluation methods that can score full sentence answers instead of relying only on short string matches. Third, we will tackle prompt sensitivity by standardizing prompts and systematically analyzing how much performance varies with different phrasings. Fourth, to avoid model staleness, we propose continuously updated leaderboards that reevaluate new models as they are released. Fifth, we plan to scale dataset sizes per language to reduce variance and ensure statistically reliable comparisons. Finally, we will expand coverage by adding new multimodal tasks such as dialogue summarization, OCR, and retrieval, and extend this benchmark to more languages, especially low resource ones, while also capturing cultural aspects to ensure fairness and inclusivity. Together, these steps will make benchmark more fair, reliable, and comprehensive.
The M5 benchmark is multilingual, multimodal, and introduces new datasets like M5-VGR and M5-VLOD. However, its main focus is still on measuring accuracy gaps between high and low resource languages. It does not really capture deeper cultural vision language challenges, and importantly, it does not handle sequential tasks, where understanding the logical order of events is critical. We propose extending M5 to include sequential cultural tasks. For example, take Diwali, a festival that involves multiple steps. Here, the task is to reorder a shuffled set of images into the correct sequence using a reference image and cultural context as guidance. This requires the model to understand not just the visual elements but also the cultural logic that underpins the order of events. Here's the correct order: first decorating the home, then lighting diyas, and finally firecrackers. This kind of task goes beyond simple captioning or Q&A. It requires both temporal reasoning and cultural reasoning, which are missing in the current M5 benchmark. So by extending M5 with culturally grounded sequential tasks, we move from just measuring accuracy to truly evaluating fairness, reasoning, and inclusivity.
Through the experimental plan of our project, the objective we are trying to achieve is we will give a model one image as a reference image, and then we'll give a subsequent shuffled images, and the model needs to arrange them in the correct order, where the parameter by which we are judging is by its cultural context. The data set will contain multiple cultural events, and the proposed data set structure is that we would have a reference image, then the shuffled images, the correct order, then the cultural tag to it, the captions defining the images, and an explanation, overall explanation with the reference image and the shuffled image. And the split that we are using as a by standard split, which is 70s to 20s to 10, train test validation split. The task we are trying to achieve are event relation inference, sentence ordering, and image ordering, where event relation inference would be like you give an image as a reference and then shuffled images, and those would be the events, and it needs to order it properly. And then there is sentence ordering, where each caption of the images are given in a shuffled manner, and it does it similarly the image ordering. Some of the baselines we are trying to use to evaluate the performance are visual/text similarity baseline, a zero-shot multimodal large language models evaluation, and fine-tuned reference-based multimodal large language models evaluation, where what we do is we train the models on our images and then we see how they are performing. And one of the common is pairwise ranking model. So the training setup, the losses are from that losses we are trying to use are permutational cross entropy, pairwise ranking loss, and list-wise loss. Then for augmentation, we use random shifting, multilingual captions, swap cultural similar but with an incorrect step. And then for evaluation metrics, we use our sequence accuracy, Kendall's tau, and Spearman correlation in pairwise accuracy. So the analysis that we are trying to get out of this project is the effect of the cultural markers, event distance, how far the shuffled images are to the reference image, and cross-cultural generalization. And we'll try to train it on some cultures and test it on some unseen ones. So we have to see if the model is able to generalize it properly. And the outcome would be a data set, a baseline model, and some evaluation. Thank you.